The topic of today's webinar is using common mode chokes to improve EMI performance in automotive data buses. I would also like to welcome Professor Arturo Mediano from the University of Zaragoza. He is an EMI EMC magician, and he will take you through this webinar. CAN, LIN, and FlexRay keep vehicles connected, but EMI can disrupt critical signals. How do common mode chokes help ensure EMC compliance? The stage is yours, Aturo.
Okay, thank you and good morning. Thank you for your presentation. I am very happy to be here in Digital Days from both electronics, and we will have a short presentation related with common mode chokes. I will be happy to answer all your questions at the end of the session. And let me start sharing the screen with you. Let me share the screen. Okay, this one, I think it's this one, X. So in theory now, you see my screen where I will be presenting some slides, and at the end of the presentation, we will be able to see a demo. Okay, we will be talking about common mode chokes. These slides will be with you later, so you can review my presentation. And we will be talking about what a common mode choke is, how common mode chokes can be able to solve EMI, radiated or immunity problems, and we will see a demo using a CAN data bus. At the end of the session, we will have the question and answer time. Well, first, this is the outline of the presentation. We will talk about what is differential mode and common mode. We will be talking about filtering, differential and common mode, how common mode chokes are relative to differential mode chokes, what are the typical basic requirements for a common mode chokes. We will see a demo with a small common mode choke from Booth Electronics. And finally, we will introduce this common mode choke in a very simple demonstration. At the end, we will be able to talk about conclusions. So let's talk about common mode and differential mode. Think you are in electronics and you are working with a system sending a signal from a transmitter to a receiver. One very simple way to think about this is that you are sending a signal in this direction. Let's think about current. Current is going in this direction, and current is returned through the, let's say, ground wire. No? So we have a red wire for the signal, a ground wire for the a black wire for the return path. Let's talk this differential mode. This is my signal, and this is because I am drawing in green color. Is desired signal. Consider that you are interested in differential mode EMI. Differential mode EMI is the current that is going in a similar way in the two wires. Usually, for example, your differential mode signal is in low frequency, let's say up to 1 megahertz or something like that, or audio signals or power supply signals. And differential mode EMI is in the high frequency range. That is because usually we filter low pass. So what happens if you are in this situation and you take a current probe? You take a current probe and you go around the two wires at the same time, you will see a current that is equal to 0 because there is no net current going through the current probe. This is a typical situation. We talk about these differential mode currents, and usually for the EMI currents, this is not dangerous because you need a lot of milliamps of current and you need a big loop to be able to radiate to the environment. Usually the two wires are one close to the other, so usually the loop is small. Obviously, you have a big loop or you have a high current, you can create differential mode radiation, but this is not so common like the next situation. In the next situation, we put a current probe, and the output of this measurement is not 0. How could we can represent this non-zero situation? Usually, we talk about common mode current. What happened? We have some kind of common mode signal going through the two wires in the same direction. And we have some kind of mechanism to have the current returning in some specific area close to our setup. Usually the ground floor, we have a metallic chassis, the automotive chassis, or any other environment that is close to the device under test and is able to manage to carry this current to the to complete the circuit. No, this is what we call common mode current, and it's really dangerous because with a small quantity of microamps, 10, 50 microamps, in the typical length of cables can radiate. No, so think about this cable like a typical signal data, or for example power supply, something like that. How we can filter these kind of signals? If you are interested in filtering differential mode, the first possibility you have is to put a capacitor between the two lines. You will be filtering low pass. The other possibility is to introduce a series inductor. A series inductor in any of both wires. Usually you are using positive and a ground wire. We don't put the inductor in the ground wire to avoid any kind of voltage drop in the ground. Anyway, we can put in a line neutral or in a differential signal the inductor in both positions without any difference. If you take the decision of using a ferrite, the difference is that with the ferrite you will be interested not only in creating mismatch like what you are doing with inductors. Remember, inductors usually will not represent some kind of losses. In ferrites, we are interested in creating dissipation. We want to kill the noise and not only to reflect it to the source. This is the way we will be filtering differential mode, with the inductor in series or with the component in series or with the capacitor in parallel. But if you are interested in filtering common mode, you have the possibility to introduce two capacitors, because in common mode you have two circuits. You will need two capacitors, and the capacitors must be connected to that kind of return path we will explain before. For example, the chassis. In some situations, the access to this chassis is impossible. So you need to filter introducing two inductors in series in both wires. The disadvantage of this solution is that usually you will have the possibility to saturate the inductors, or for example, you will be able to create a signal integrity problem for your differential mode signals. The solution for this problem is to introduce a couplet inductor. A couplet inductor is when you take one core and you coil or wind the two wires in the core in some specific way. In this way, the component ideally is invisible in differential mode and is presenting impedance for the common mode. The alternative to inductors usually is to introduce a ferrite. You can introduce one ferrite in each wire, or better, you can introduce one ferrite around the two wires at the same time. The difference is that usually with ferrite you will be focused in creating losses. And the second solution, the ferrite around the two wires, has the advantage that you will not saturate the ferrite like is the possibility in the first solution. Remember, with the ferrite, with two ferrites in the two wires, you will be additionally creating perhaps some kind of signal integrity problem, because two ferrites, one in each wire, is not invisible for the differential mode signals. But a ferrite around the two wires is invisible for the differential signal, so you will not be creating signal integrity problems. In our presentation, we will be interested in using the common mode choke like a good solution to reinforce the EMI behavior of the circuit without introducing signal distortion, and considering that it's not possible to introduce capacitors that are connected to the chassis or to some kind of retro path. Okay, so how is the difference between differential mode and common mode chokes? I will be using these pictures from Booth Electronics, not because we are interested in this kind of chokes, but it's interesting to see how is the way we build these components in the picture. They are for low frequency applications, for power supplies, for example, but it's very useful to explain the idea. In the differential mode choke, you take one core and make several turns around the inductor. So you obtain some kind of microhenries or millihenries, and the manufacturer will give you the impedance or the insertion losses of the component as a function of frequency. Remember that in this situation, you can have losses created by reflection, the inductive part of the component, or losses created by dissipation, is the resistive part of the component. What is a common mode choke? In a common mode choke, we have two wires around the same core. So the two inductors are coupled. These inductors are coupled. If you have the perfect coupling, I mean, 100% of the magnetic flux from one of the coils goes to the other coil. The advantage is that this component will be invisible for the differential mode, but you will be introducing some impedance for the common mode signals. The disadvantage is that the disadvantage is that real world components have not a perfect coupling. You have some kind of leakage, let's say 2%, 3% of the nominal value of the component. This leakage, this flux that is not picked by the second coil coming from the first coil, this leakage created the possibility to introduce some kind of differential mode filtering. That means the component is not invisible for the differential mode. This is good in the idea that with this leakage inductance, you can filter differential mode noise without an additional component, but this is bad because you can introduce some kind of saturation if your desired signal is big enough. The manufacturer will give you the idea or the information about how is the impedance or the insertion losses of this component relative to the common mode. That means the area where you are interested in using this component, or the differential mode that is created by the leakage effect. And then you can evaluate in the graph at what frequency this component could be useful. Remember, to understand how this component is designed, you take the wire, you introduce in this way, and usually the symbol for this component in schematics is something like one coil, the second coil, the core they share, and we put two dots at two ends representing that this is a common mode choke is winded in this way. So differential mode currents in this direction create a magnetic field in this direction, and the current that is returning in the opposite direction is creating a magnetic flux in the opposite direction. So the magnetic flux inside of the core is in theory equal to 0. Remember, this is not really true because we have 2%, 5% of the magnetic flux that is not sorry. If you go to the same core and you evaluate what happened with common mode currents, you can see that for common mode currents going in the same direction, the magnetic fluxes go in the same direction. So the idea is that at this in this situation, for this common mode current, you are introducing some kind of impedance. So you will be able to filter the signal without distortion for the differential mode signals. Well, in this idea, how is the idea of selecting a common mode choke for your application? Obviously, you will need to evaluate how much is the attenuation you need for filtering common mode in your application. And additionally, you need to take care about how distortion can be introduced in your signal if you have some kind of differential mode filtering effect. Remember, I am considering that my signal is going in differential mode. Well, so consider that you will need to evaluate how much is the attenuation you need, how is the frequency range you need to filter, how is the frequency range for your desired signal, and the possibility to saturate if your desired signal is bitter. So let's see one example. This is one of the small common mode chokes from Booth Electronics for high speed the signals. You can see that this is a very small SMD component. It's fully different to the previous chokes I have been using to explain the idea, but they are winded in exactly the same way. So we can see that the inductance for the common mode is around 51 microhenries. And if we evaluate how is the response of this filter following, for example, CPR17 standard, we will be able to identify that this common mode chokes has a high impedance at around 100 megahertz with an impedance value of around 8 to 9 Ks. Obviously, we have some kind of differential mode filtering. Remember, the common mode choke is not invisible for the differential mode signal. We have some leakage, and this is what we see in this picture. You see 3 different graphs because I am using RedExpert, is the tool from Booth Electronics that is able to compare different components in the same graph. Okay. Remember that the component I will be using in my demo is this one, 7H4234510. This is a 51 microhenries inductor. So let's try to see how we will be doing the demo. In my demo, we don't have a lot of time. I will be using a temperature sensor, humidity and temperature sensor that will be read by a microcontroller. And we send using a CAN bus adapter a signal at some centimeters in length, 1 meter more or less, because it's a small setup on top of the table, using a twisted pair that is 120 ohms in characteristic impedance. Remember, this is the quasi-differential signal. This is not a total differential signal. CAN is a protocol that is quasi-differential, and we have a 120 ohms characteristic impedance. It's a uniform transmission line. Because this is a uniform transmission line, you have a long distance, you will need to terminate to avoid reflections with a resistor that is 120 ohm in value. Then we have a CAN bus adapter, we have the microcontroller reading the signal, and we will send in the information to the computer so we can read temperature and humidity continuously. The idea is that we will be using an RTO6 oscilloscope to see how my signals are in the twisted pairs cable, and additionally, we will be able to measure the common mode current of my activity. Remember that in ideal situation, the common mode current must be equal to 0, but in a real application, this common mode current usually is not 0. You have some kind of microamps going in common mode, and the result of this effect is that the cable will be radiated. Remember, with 10, 15 microamps of common mode current, probably you will be failing at 3 meters or something like that in a typical radiated emission standard. My common mode choke will be introduced in this way in the demo. So I have 2 small jumpers, and with the 2 small jumpers, I will be able to short circuit the component to see the difference with and without the common mode choke. So let's go to the cameras so you can see how I will be using. The first step is to show you that you can measure how much is the oh, sorry, let me go to the camera. Wait a moment, please. Wait a moment. Here, I will show you the camera. It's starting, sorry, this way. Okay, solid camera. And now I will be using the camera here. Okay, this is the camera. I hope all of you see. This is the transmitter. This is the receiver. And here you can see some kind of cable I am using here. Let me show you with the camera how is the measurement of my common mode choke. I have a setup here, and my common mode choke is here to be able to evaluate. So let me go to the software of the Bode 500 instrument. With this instrument, I will be measuring the impedance, the common mode impedance of my component. Let's run the test. You can see that this is the impedance. It's similar, it's exactly equal to the impedance we have seen in the data sheet from Booth Electronics. Remember, I was introducing this graph here. Is this the graph in the bottom of the screen? This one. If we go to the blue trace, is the total impedance. We go to the measurement, and we see this total impedance. This is reactive and resistive part. If we go to the resistive part, we can see that in the top of the impedance, we have basically a lot of resistive effect. This is important because this kind of common mode chokes had the advantage of reducing radiated emission because they offer some kind of losses in some specific frequency rate. In this case, in the around 100, 200 megahertz. But additionally, the common mode choke is offering some kind of inductive value. This is the reactive part of the component. You can see that in the low frequency area, we obtain an inductive effect, but in the peak of the signal, we have inductive and resistive effect. Okay, so let's go again to the camera. You can see here that my demo, let's go to the camera here, is using these signals, and I will be using my RTO oscilloscope to measure the signals in the CAN base. I am not doing this correctly, so I hope my students are not seeing this, because you know we cannot use this kind of pigtails, but for the demo purposes it's enough. Remember that to see the signals correctly without distortion, without any kind of ringing, the pigtail of the probe is not a good strategy. Anyway, if you don't have this PC board prepared to measure without the pigtail, it's impossible to do this, okay? So let's go to the screen of the oscilloscope here. This is the screen of the oscilloscope, and let's switch on my device, on and on, okay? And you can see in the top of the screen, we have the height component of the bus, and in the green color, you see the low part of the bus. Now I can open the monitor in the computer, so you can see here, okay, you can see here that I am receiving the the temperature and the humidity. No, temperature 25 degrees, humidity 47%. Okay, so this is the idea. I am sending information with a signal more or less distorted. Remember, for example, that if I introduce the pigtail, if I disconnect one of the ground wires, the ground for the second probe is obtained from the ground of the first probe, and this is a really bad situation for measurement of the signal. You can see that we have a lot of additional noise, that if I introduce again the connection of the ground pigtail, the noise, the signal in the yellow trails will be better. Now, okay, you can see that it's better now, no? So many of the artifacts using this kind of signals is related with how you are measuring, not, they are not really in your signals. So let's remove here the probes, and let's consider how is the common mode current in my cable. I will be using a tech box current probe. Remember, this is the current probe I can use to measure how much is the common mode current in this cable. The common mode current in this cable must be 0. If not, the cable can be a good antenna and to radiate in the VHF range, typically from 30 megahertz up to 300, 400 megahertz, is the most typical area where your cables will be creating problems for you. And I am going to introduce this current probe in channel number 3 of my oscilloscope. So now I will recover from my instrument. Let's go to the oscilloscope. Let me, no, this one, recall. I am recall the, let me show you the screen of the oscilloscope so you see what I am doing. I am recovering from my oscilloscope how is the signal in common mode. This is only a setup that I have prepared to avoid having problems. So this is the signal in common mode. Remember, we see in the vertical scale millivolts, and these millivolts are related with the microamps we have in the in this circuit. No, we have a common mode current of microamps, and we see in the oscilloscope some kind of millivolts in amplitude. You have the calibration of the probe, you can convert these millivolts in microamps. So let's see what happens if we introduce our common mode choke. So let's go to the camera and let's try to introduce here my filter. No, I'm going to disconnect here the twisted pair, and I'm going to introduce here my common mode choke. This is a prototype, so it's not really nice, but I hope for the demo is enough so you can understand my ideas. Okay, so you can see here, I have the common mode choke. Let's see this way. This is the common mode choke, and you can see here 2 jumpers, blue color, that are can create some kind of short circuit of the common mode choke. If I remove the jumpers, the common mode choke is in place. So I only need to connect again my twisted pair, but now I am introducing the common mode choke in series. Remember that this is a situation where I am not able to introduce capacitors from the lines to the chassis, or the introduction of the capacitors from lines to the chassis can distort, can create signal integrity problem in my circuits. So let's see again the screen of the oscilloscope. You see, this is what I have without the common mode choke in place. And now I am going to remove the jumpers so the let's increase the amplitude. This is without the common mode choke. This is with the common mode choke. 1, 2, 3. Okay, you can see the reduction. If we go to the FFT, let's recover some signal from the oscilloscope. If we go to the FFT, this one, okay, you see in the top of the screen, you can see, let's change the color, change the color in the lower signal. This is, for example, this is channel, the math channel. Okay. This one. I don't know why. Okay, cancel. Sorry. Here is the math function. Is the math functions channels. Math one. This one. Probably it's better in this color, in yellow color, so all the people can see better. Okay, and you can see how now is without the common mode choke. This is with the common mode choke. You can see the reduction. Okay, this is without the common mode choke. Okay, sorry. I know. Okay, let me see. Now, here, and this is with the common mode choke in place. You can see the peaks of the emissions are reduced around 10 dBs. Okay, so this is basically the idea. And we are going to the end of the session. The idea of this demo, let's go to the screen again. The idea of this demo, remember, like a conclusion, is you have your system here, system number 1. You have your system number 2. You have a big transmission line. In this case, it's a twisted pair. The idea is that you have a common mode emission. This common mode, typically between 30 megahertz and around 400 megahertz, could be microamps of current. This current is going in this direction and create radiated emission. It's the same if you are interested in immunity. Immunity, you are receiving the electric field, and the electric field is inducting common mode currents in the cable. In this case, the idea is to introduce in the middle something that is filtering low pass. So you introduce a common mode choke because it's invisible for your signal, but it's introducing impedance at the frequency you want to remove. Remember, this is not a broadband filter, so you will be only focused in reducing the area, like you have seen in the demo, only the area around 100 megahertz, no, between 50 megahertz and around 200 megahertz. And that's all. I think it's time for questions. Sorry for going very, very fast, but we have a limited time, and I will be happy to answer any question you have. So.
Interesting presentation. It was a good one. So
thank you.
I'm just uploading the handout. You should be able to see it right now. So for everyone who can download it later or now. Right. So let's have a look at the questions. The chat was like pretty well used. And I think there was an interesting question from Benedict. Maybe we can take a closer look to that one and you can answer it. I will pin it for you.
Okay. Oh, we start with...
Can the CM choke be used when there's also power transferred over the same two wires? As example, in a SPE, PoE kind of situation.
Yes. I think I understand the question. Yes, because if you consider that you are sending into wires your signal, let's say this signal, and additionally you are sending some kind of DC. If you are sending DC, the DC and the signal go through the low pass filter. That is, the common mode choke is invisible for DC, so you can send signal. This is the opposite to using this. You put the transformer in this situation, you are not able to pass DC. But if you put the transformer in this direction, this transformer is invisible for DC, for your power.
Perfect. Thank you very much, Aturo. Also for the drawing. I think that was easy to understand. I'm not sure if this is a follow-up question, but Carl questioned, will this help keep our vehicle networks stable as data rates go up?
I don't know what means stable, because stable is a very general idea, but if data rates go up, the most difficult part for these components, like with using capacitor, is the possibility to avoid distortion of your signals. No? But obviously, if you have a good filter, usually your setup will be more robust. Okay, but this is all I can say. Sorry.
Oh, that's fine. Thank you very much. Okay, let's see what else we have. Here's one of the new ones from Massimo. Hello, regarding systems with a lot of single-ended lines and one GND, like for example a complete RS232, is there any best practice for reducing CMN without using CM chokes on external cable?
Well, I suppose that in this question we need to introduce something additional for these people, that is, and you need a low-cost solution, no? Well, if you have a lot of common mode, the idea is not to create common mode. This is the best strategy. If you don't create common mode, you will not need to filter common mode. And sometimes this is not impossible or is very difficult. So the first strategy is this idea. You create common mode when you have a change from a single, from a balanced circuit to an unbalanced line, or the opposite. I mean, if you are using a microstrip signal in your PCB and you introduce this in a cable, this is an unbalanced signal. So the idea to create common mode is that you create a lot of common mode if you introduce this unbalanced signal in a balanced line, for example, a twisted pair. If you use a twisted pair and your signal is unbalanced, you have more probability to create common mode. So for an unbalanced situation, for an unbalanced signal, instead of using a balanced line, the idea is that you need to use something like, for example, a coax cable. A coax cable is a transmission line that is unbalanced, and the common mode will be very low. In the opposite way, if you have a signal that is coming in a differential way, okay, you have a high and you have a low, because this is a balanced signal, the good strategy to avoid common mode is to introduce this in a balanced line. I mean, for example, a twisted pair. And then your common mode will be reduced. If you are not able to do this, the only possibility to minimize common mode is to introduce common mode chokes or to make some kind of filtering with common mode capacitors. I mean, you will need some kind of capacitor from one line to other line, to the other line, to the different line you have, connected to the ground plane that you have, like the return path. And this is something impossible. Sometimes this is impossible because this return path is not accessible. Okay?
Wow, Aturo, thank you very much. I'm very impressed by your answers. I also got a next great question. I think
important. Sorry. It's important to clarify from a previous answer that many people think that common mode is created, especially when you have the mismatch and you have reflections. No, you can have common mode if you have reflection, but this is not the dominant effect. The dominant effect is the change from unbalanced to balanced or the opposite in your signal. Okay, let's go. Sorry.
Perfect. Let's keep that in mind, and it will be in the recording. So there's a next great question from Marian. It's how to deal with situation when you need to use common mode filtering for multiple signals, buses, power outputs, and also need for one reference point for some of them, like GND, and another device connected with our EUT via long cables.
Well, let me think. You need to use common mode filtering for multiple signals and So you need one reference for some of them. Okay, let's see if I understand. You have a system, you have another system, you have several lines. Let's draw this in red, blue color, and green color. You have the different signals, and additionally, you have a ground line. So in my understanding, your problem is that you have here a situation where the probe is giving a common mode current is not zero here. So you will need to filter all of them with series impedance, including the ground signal. This is the only possibility to reduce the problem. Depending on the frequency range, perhaps you can introduce a ferrite in series, or perhaps you introduce in your PCB a small ferrite bits in series with each line. Remember that introducing impedance in the ground wire not always is a good strategy.
Okay. Thank you very much, Aturo. Marian, I hope this was a question or the answer you needed for your question. If not, just let us know, and Aturo will be happy to answer it. So let's have a look at the time. I think we have still time for some more questions. Okay, here's one from Murad. How can I distinguish CMC and DMC in PCB?
I suppose distinguish means how you can measure. In a PCB, it's not easy. In a PCB, you have not the possibility to introduce your current probes to make the test, and you cannot separate with the free probes. So it's not possible. It's not possible. But in a PCB, no, it's not possible. It's not possible.
Okay.
In my opinion. In the PCB, you have differential mode.
Not possible.
Sorry.
That's also not.
In my opinion, it's not, or at least I don't know how to do that.
Yeah. You are honest. That's nice. So now the next question. From Bison, I hope that's right. I'm sorry if I pronounce it wrong. How common mode choke works in USB bus?
That is the same. Is in USB bus, you have your signals. You are interested in not distorting the differential signal, the data, and you introduce the common mode choke to introduce impedance for the common mode, and being invisible for your signal is the same. You have very nice application notes in the Booth Electronics website, where you can find how to introduce the common mode chokes in the USB signals, introducing additionally some kind of protection like with TBS, with diodes to avoid ESD problems in immunity. So you go to this application note. If not, let me know and I can look for you the application notes from the website of Booth. Okay, but it's the same idea.
Thank you, Arturo. Also, you can use our search button on our website and look for the application note. I think it's time for our last question. So here's another one from Carl. Can CMCs really make a difference in noisy environments?
Yes, I think common mode chokes are good components to increase the immunity of systems. Of course, in my opinion, both common mode chokes and ferrites. I have reading from some time ago many people writing in social networks or in the website that ferrites are dangerous or common mode chokes are not so useful. In my opinion, they are very, very good components like capacitors or like any other component. The only thing to do is you need to work with them correctly. You need to understand the data sheet, the limitations, where is the saturation, what you are introducing. You are introducing inductance or resistive effects. But common mode chokes are a really interesting solution to minimize both emissions and immunity for sure.
Perfect. Thank you, Arturo. You did a great job with the presentation and the question and answer session. We are finished with this webinar. If there are any questions left, and I saw a lot of them still in the chat, we will answer them afterwards via email. And thank you very much for your attention. And I hope you enjoyed our webinar. Also, many thanks for Arturo one more time. And I just uploaded a link to the Digital E-Days. If you are interested in any other sessions, feel free to register now and click on the link. Thank you very much.
Okay. Thank you. I'm sorry for going so fast. Bye-bye.